Okay, previous lesson, guys, we obviously talked about what is a function and how to identify a function, looking for each x having one exclusive y in a table of values or the vertical line test in a graph. And yesterday we looked at what is an inverse, and today we're going to look at what is an inverse function. Everything has an inverse, but their inverse may not be a function, okay? And we're going to show how to test for invertibility. And what invertibility means is it means the inverse will be a function, okay? That's what invertibility means. And if the inverse of something is not a function, how do we restrict the domain so that the inverse will be a function? That's what we're looking at today. It seems really confusing, but it's actually not as bad as it sounds. So here we go. We did 1 and 2 yesterday. So what we're going to do is we're going to look at number 3 and 4 today. Yesterday we gave you the graph. Today we're going to make ourselves graph it. Now remember, this should be super easy to graph because that is like x plus 0 quantity squared plus 3. So I have, when I'm looking at graphing it, okay, I have the vertex at 0, 3. So I can plot my vertex, and if you don't like what I'm doing, putting it in vertex form, well, then you can pick a bunch of x's and plug them in and find out what the y is. But once we had vertex form, remember we 1,4,9'd it, and we reflected the points. So now I have the point 1, 4 and negative 1, 4. And if I went over 2, I went up 1, 2, 3, 4, and I reflected that point across. So that gives me 2, comma, 2, 4, 6, 7, and negative 2, 7. Well, that is the parabola that we're talking about right there. Now notice, this is a function, but now notice when I graph its inverse, will its inverse be a function? Which means I'm taking the points here, x, y, and that's a bad y, and I'm going to reflect them, or I'm going to invert them, 3, 0, and 4, 1, 4, negative 1, and 7, 2. When I say inverting, I'm simply reversing the order pair. I'm swapping x and y like we said in the previous lesson. Now I'm just going to plot these points. 3, 0, and 4, positive 1, and I also have 4, negative 1. And I have 4, 5, 6, 7, 2, and I have 7, negative 2. So notice when I graphed the inverse, is this a function? And the inverse of that is not a function, right? Because this red one does not pass the vertical line test. However, it is said to be the inverse of the blue one, okay? Because all these points are reflected across that line y equals x. It is the inverse. It just so happens to be the inverse of this entire blue function is not a function. And there's a reason why it's not. There's a test we can put on it, and that's what we're going to learn today quick, testing for invertibility. And now we're just going to come over here to this one. Well, I'm pretty sure everybody can graph that line. It's a line with a y-intercept of 4 and a slope of negative 2. So I go down 2 over 1, down 2 over 1, okay, down 2 over 1, down 2 over 1. And I can graph that little bugger, and I want to make sure I'm going to graph that little squirrel in a blue line. So I'm going to grab it, I'm going to graph it. Probably should have made it solid, but that's okay. Whoa, I didn't want to do that. Get rid of that little bugger, delete that little bugger, and let me grab this guy. Stretch them up, so there's my line, okay? And if I wanted the inverse of this, notice we plotted the points. I'll keep blue to blue. We plotted 0, 4, and we plotted 1, 2, and 2, 0, And the last, I mean, we did a bunch of them. We also did 3, comma, what is that one? -2? 3, comma, -2. Well, if I wanted to graph the inverse of that, I'm going to graph 4, 0. I'm going to graph 2, 1, 2, 0. I'm just going to invert or flip these points. So I'm going to say 1, 2, 3, 4, 0. And I'm going to say 2, 1, 2, 1. And I'm going to say 2, 0. And I'm going to say -2, 3. And I can see those are lining up in a line, which they should. And I'm going to go here, and I'm going to go here. I'll just leave it dashed and be happy with it. And this line is also there. So the red one is the inverse of the blue one. Okay. Also, before I do anything else, notice the blue one is a function, and the red one's a function. They're both a function. They are inverses of each other graphically because I can see they reflect themselves across that line y equals x. Notice this line y equals x where these two functions intersect. Notice they intersect on that line. Kind of nifty. And number 4 is invertible. Number 3 is not invertible unless we restrict the domain. What are we talking about with that? Well, here we go. Next page is where we're going to discuss that portion of it. Okay? Use the graph to answer the following questions about each one. Okay. So, is this black graph a function? Yes, it is. How do we know it is? It passes the vertical line test. Okay? Passes the vertical line test. Is this graph invertible? Well, I don't know. Let's check it out. So I have this point, 1, 2, 3, 4, 0. So I'm going to want to plot 0, 4, right? And I don't know, this point up here is 1, 2, a little bit. Hold on, Kruger, you got that all jacked up. I got the point -4, 0, excuse me. And I have a little bit more than -2. I'm going to call that -2 plus. And that's going to go all the way up to about 8. And if I invert these points, this guy is going to go to 0, -4, right? So 0, 1, 2, 3, -4. I'm going to go to 8, comma, -2 plus, which is going to come down 1, 2, 3, 4, 5, 6, 7, 8. Actually, that's 10. I'm sorry. That's 10. -2 plus 10. So this is going to be 10, -2, a little bit more. So I'm going to come over 10. I'm going to go down -2, a little bit more than -2. And I can see this little half of it. Okay, how about the other half of it? Well, this is going to take me over 1, 2, 3, 4, 5, 6. That's going to be also -6. A little less than -6. Because I'm at 1, 2, 3, 4, 5, 6. So a little bit less than -6, comma 10. Well, if I inverted that point across, don't get all whacked out on it, it's 10, comma, a little bit less than -6, because I'm ballparking. I can't find the exact thing on here, so I'm going to come over 10, 1, 2, 3, 4, 5, 6, a little bit less than that. So there's that. This is going to kind of come down like that. Okay? Well, is it invertible? I just graphed the inverse of it, and I know it's the inverse of it because I can kind of take a little gander here, and I can see the reflections across that line, y equals x. Is the graph invertible? And as that thing underneath it says here, this is really asking if the inverse of the graph is a function. Is this blue one a function? No, it is not a function. Okay? If it's not, can we restrict the domain of the black one up here to allow the inverse to be a function? Well, what that means is right here where my vertex is, can I restrict the domain, like let's say I just pick this half, and let me say, restricting the domain, say, hey, this original function right here, this is only going to be good for x's that are greater than or equal to -4, because that's where I cut it off here at -4. And let's envision in our heads, we cut it off so this isn't even on here. Is that red piece still a function? And it is. Now if I graph the inverse of that one, what does that do? Well, that is kind of getting rid of, if I got rid of that left side, I got rid of that half. Well, is it a function now? And the answer to that would be, yes, it is a function now, because now this blue one passes the vertical line test, okay? So what we did is we restricted the domain on this original black one, and I cut it in half, and I graphed the half I wanted to use, that red one, and I made the domain, here restricted for the original function. And what that does, it should make sense, okay? That's an even one, so I can't put negatives in there too, but is that there? So let me just kind of get at this here. And what test was used on the original graph to see if it was a function? I wrote that up here. That was vertical line test. And is the test for a function reflected over the line y equals f? If I reflected a vertical line across the line y equals x, what type of line does it become? Well, it becomes a horizontal line. Okay? And what that does is that brings us in here. Does using this type of line on the original graph help describe if the inverse is a function? Well, the answer to that is yes. If a horizontal line, okay, if a horizontal line intersects the original function in more than one place, then the inverse will not be a function. Just like up here, if I would have taken a horizontal line on the original black one, I intersected it in two places, correct? I intersected it here before I cut it in half. I hit it here and I hit it here. And then that's what I had, which makes this vertical line, makes both halves. Well, after I restricted it, after I restricted the domain of it, and I erased the whole left side of it here, I'm like, it's not there. When I reflected it across the line y equals x, if I got rid of the left half, well, that gets rid of this half. And then notice that original function, after I restricted its domain, it only hit it once, right here. Therefore, it made this one on the other side, it allowed that one to pass the vertical line test. Okay, so that's what the horizontal line test does. The horizontal line test on the original function, if it passes that, touching it in no more than one place, then it is a function. But if it hits it in more than one place, okay, then the inverse will not be a function. So that's what we were looking at here. So from there, we got two examples, and that's it. So is this black graph here, is that graph a function? And the answer to that is yes. Why? It passes the vertical line test. That's why it is a function. Is this graph invertible? If this graph is invertible, it's going to pass the horizontal line test. Okay? So first and foremost, when I took it to see if it was a function, it passed the vertical line test. Okay? And now that it passed the vertical line test, they're asking me a whole new question. Is it invertible? If it's invertible, well, now I want to see, does it pass the horizontal line test? Well, if I took that, am I ever hitting that graph in any more than one spot? And here it gets a little sketchy, but if you zoom in on it, I'm only on it in one spot. It'll be very, very obvious when you hit it in more than one spot. Is the graph invertible? Yes, it is. Okay? And I knew it is because it passes the horizontal line test. Okay? If it is invertible, I do not need to do anything with restrictions. So because that one's invertible, I'm all good. When I look over here at the next one, now also, check it out. What would the degree of this function be? This would be some odd degree because my end behaviors are opposite. Remember that. And then number 3, when I check out number 3, I slid my whole window down. When I look at number 3 here, okay, is the graph a function? Well, that's really asking me, does it pass the vertical line test? Does it pass the vertical line test? And answer to that question is, yes it does. Is the graph invertible? Great question. Well, if it's invertible, when I take my horizontal line here, notice how it's hitting it in more than one spot. Is it invertible right now? Right now, no, it is not, because it fails the horizontal line test. So because the answer is no, how could the original graph be restricted? Where could we cut that graph in half so that the inverse will be a function? Notice also this is an even degree function. And all even degree functions, somehow, some way, they have symmetry across the y-axis somehow, okay? And notice also if I came in here and I said right here, if I restricted right there at that red dot, and I envision this whole left side of that graph were not there, does it now pass the horizontal line test? And answer to that question is, yeah, it does now. I can't get that. There we go. It does pass it now because the whole left side I scribbled out is no longer living to you. It's gone. So where did we restrict that? Well, we restricted that by saying x had to be greater than or equal to 0. And if I restrict it there, now it is invertible. It is invertible with that restriction on it. Okay, but I only have half of the graph then. So if I keep going down and I look here at the end, okay, I don't have to keep, it doesn't matter which side of that function I keep. I can keep the left side or the right side. It does become invertible then. But what type of functions were invertible? Well, odd functions. Actually, I should say, I'm not even going to say all odd functions are invertible. I'm going to cut that off, but I'm going to say for sure even functions without restrictions. Even functions without restrictions at I don't want to say at either. I want to say are not invertible. Must restrict at vertex. Okay, and I don't want to say all odd functions are invertible, but some odd functions are invertible without restrictions. what that means is any function, okay, I'm going to leave this here too, and I'm going to say all functions that are one-to-one are invertible. And what one-to-one means, there is no repetition of any x or y values. Okay? And I just want to sum it up. You're ready to give a shot at your homework, but I want to follow up and I want to say some odd functions because we've graphed many odd functions that kind of looked like this. And notice that would not. It's a function, but it's not invertible. Okay? If I restricted it from here, cut it off, and I only kept that half, and I got rid of the left, it would be invertible. Okay? If I restrict, there's all kinds of restrictions I could put on it. We're not going to get that deep into it, but that's why all odd functions are not and some are. That's an odd function, it's invertible. But all even functions, my end behaviors have to be going the same way. All even functions have to have restrictions. Okay, give your stuff a shot.